Okay, we have a live stream. Okay, to not punish you guys who were on time, I think we start and rather finish on time again. Good. Welcome back. Brief recap. We looked at the hardness part of parameterized complexity. How can we prove that a problem probably does not have some fixed parameter tractable algorithm? And we looked at some first attempts. First of all, we had parameterized reductions. That's useful. This is going to stay. So it's a reduction where we transform one problem into another so that a yes instance of one problem becomes a yes instance of the other problem and vice versa. The transformation is computable with an FPT running time with respect to this parameterization of the input problem. And then it has to be parameter preserving, which means the parameter of the output that we generate is bounded by a function of the parameter of the input and not depending on the input size. Then we write this less or equal FPT to indicate that this L2 kappa 2 is in a sense harder than the other one, where harder means any FPT algorithm for the harder problem implies one for the easier problem. Okay, we've seen examples of reductions that either are or are not parameter preserving. That's usually the property that breaks if you take classical reductions, as we discussed at length in the tutorial yesterday. And we've seen a first attempt. Just to pull up that definition again, para-NP was the class of problems where we can take FPT time, but on a non-deterministic Turing machine. And it turned out that is not the right definition to distinguish cases where we have an FPT algorithm from cases where we don't seem to find one, because it was too strict. We basically had this result that if something is para-NP hard, then it kind of immediately is NP hard for a very restricted subset, namely with a constant parameter. So most interesting problems cannot be para-NP complete, and so we still cannot distinguish between these problems, for which it seems very unlikely that they have a fixed parameter tractable solution, from others where we have this, and yet others where it's even more hopeless. But these cannot be para-NP complete, I guess, unless P is NP and nothing matters. So what we'll look at today is the fix, how to construct a different complexity class. And for that, we'll take a little bit of a detour, but I kind of tried to cut it to the necessary bit only. In the next section, we'll look at a new proposal for a complexity class against which we can try to prove hardness for parameterized problems, in the hope that this is a bit more suitable to show that certain problems are hard, for which that isn't a trivial statement. For the P coloring, graph coloring problem, we had this fact that it's para-NP hard, because it also is hard if the parameter is fixed at 3. So here we want to try to include problems where this alone is not the case. So a fixed parameter doesn't make the problem hard, but it overall doesn't seem to allow an FPT algorithm. For technical reasons, it seems working with Turing machines for defining this class is not convenient, or causes more problems than it solves. And I mean, in a way, this was just what I said before. Para-NP seemed like a natural definition, just replacing deterministic FPT time by non-deterministic FPT time. But it is, in a way, a too powerful class. So hard problems are too hard in our case. And for technical reasons, Turing machines seem not to work well. I think there's no great justification other than that. So we'll look at some slightly different models of computation, but also are fairly easy to work with. One thing I wanted to say here is we will restrict our study here. We'll look at parameterized complexity classes, to the key tools to prove that a problem is unlikely to have I guess there's some word missing. Is unlikely to allow an FPT algorithm. If you want the structural complexities, say, study finer distinctions between problems, you could go further than we go. On the other hand, I also didn't want to just use reductions. One alternative in complexity theory would be you just nominate your favorite hard problem, the one that seems convincingly hard to you, and you show that the other interesting problems you care about can be reduced to this problem so that they are harder than a specific problem. So here, for example, we could just say that the parameterized click problem seems hard. Let me use the proper font. And then try to reduce problems to just to that. So we could try to establish, say, let's write it properly. So you show that some problem you care about is at least as hard as the p-click problem, and then just stop there and say, yeah, it seems nobody knows how to solve p-click, so I'm going to stop looking for fixed parameter tractable algorithms for A. It seems unlikely that they exist. But this is a much weaker statement than what we are used to from classical complexity theory. Normally, we also do just a single reduction like this, but we pick a problem here that's NP complete. And so after we've done that reduction, we don't just know that some new problem A is harder than some specific problem that we picked, maybe 3SAT or whatever reduction partner you used. But because that problem was NP complete, you know, this new problem A is harder than all the problems in NP. Harder in the sense of everything reduces to it. And that's a much harder, a much stronger statement, because it means your new algorithm doesn't have this algorithm, your new problem doesn't have this efficient algorithm unless all of these others also have one. And if we were just to do this, it would be a much weaker theory. We would only relate problems to individual other parameterized problems. So that's the two extremes. One would be go full on the complexity theory and study all the classes and their hierarchies, which might be suitable for a specialized complexity theory class. But I feel here would lead too far. On the other hand, I didn't want to just say, okay, let's pick a magic problem like p-click and just proclaim that this seems hard. So I'll try to do some middle ground. The implication of that is that some of the definitions are not the original definitions of the classes we were studying, but rather they're alternative characterizations that people have proved about those classes. And they overall make a round picture, but they don't exactly correspond to the sources where it's taken from. It kind of combines different results. It's just a little disclaimer I wanted to put out there. So if you read up on some of these details or dig a bit deeper, you'll find that I'm renaming a few things. But the essence is the same. What we want is some hardness class. And let's name the beast. It's going to be W1, which is not WP that we'll see in this chapter. So there's one more step to go. So the goal will be to prove W1 hardness. And I'm not saying completeness, because for some problems that wouldn't be true. We'll only show hardness. For some problems, it's also completeness. For others, you would have to go a little higher to W2 and so on. But that part is this first bit where I'm not so interested in. If a problem doesn't have an FPT algorithm, how exactly it fails to have one, I think is slightly less interesting than the fact that it doesn't admit one. We'll maybe see some other techniques later. The board is really annoying. Should have told me that you can't read the last line. Okay, that's for the setup. So if we're not looking at Turing machines, what else is there? Well, many things, but actually we see an old friend again. For some of you, it's the random access machine. So if you want, we can say it's the word RAM. Now there's an important additional letter here, the NRAM, which stands for non-deterministic, right? So it's a word RAM, which just means it's a machine that has a long array of memory cells. Each memory cell can hold W bits, and we're supposed to interpret this as a number, an integer. And we can do the usual arithmetic operations on integers. We can also do bitwise operations, like a bitwise and all these things. So just to recap there, we've had it at the very beginning. So there's a large memory with just indices. And the important part is that these are really also numbers. So you can use indirect addressing. You can use the contents of one register to tell you what memory cell to read next. So you can do pointers. Right? So we have these. This is essentially unbounded. It's as big as you want it to be. And you have a finite number of registers. Say 100, it doesn't matter exactly what the number is, but it's fixed and independent of the input size. And then you have operations for loading pieces. You can read a memory cell and load it into a register. You can write back to some memory cell, and you can give the address that you're writing to as the content of another register content. And you can do arithmetic operations, and you can do the usual comparisons and conditional jumps. That's just a reminder of what the word RAM model is. Now, there's an additional operation. That's the important bit from the N. We can non-deterministically guess a number. So there's a new operation. It's a fictitious operation that real computers cannot do. But you can say this register non-deterministically should now contain a number between 0 and some upper bound that you give by another register. And this is the machines that we're allowing our algorithms to use. Now again, remember, this is like NPs, like non-deterministic Turing machines. You're not supposed to build this machine. This is an overly powerful model that we're gonna work against. Then we'll say such an NRAM decides a parameterized problem, language and parameterization, in the usual way, like how do we define acceptance? I guess we have some output register, and that contains a 0 or 1. And we call such an NRAM kappa restricted if its running time is FPT for the input. This part is the same as for Turing machines. Also the space, I mean here, okay, memory cells, I would really want to say. The space usage is kind of following from the time. You don't even have time to touch more than this. But it's maybe less obvious than in the Turing machine. We also put a bound on the numbers in the memory cells. So in a way, you could control this via W, but it's more convenient to directly just say the numbers that we have are bounded in terms of the parameters. So in a way, the traditional is just log n. With a parameterized problem, we would say W can be a power polylog n, and sorry, it's log of a polynomial. That's just log n, and some arbitrary function of k. If you take the log here, it doesn't really make a difference. Okay, so these are relatively natural things. That's just what an FPT algorithm means on a word RAM as opposed to a Turing machine. But then there's this second requirement, which is important, kappa restricted. The number of non-deterministic guessing steps, these new operations, the fictitious magical operations, they're bounded in terms of the parameter. You cannot do arbitrarily many of those steps. Okay. So how does this compare to Turing machines and FPT running time? Especially if you compare it to para-NP. There we didn't have step 2. We said non-deterministic Turing machine with a certain running time, but it was allowed to do a non-deterministic step each time it does a step. And so this restriction 2 here is the key difference. Now you could have tried to do the same in a Turing machine, restrict how often it does a non-deterministic step. The problem there that makes this inconvenient is that in a Turing machine, the non-deterministic guesses are actually finite, they're bounded. For a given machine, there's a given number of states, and everything's finite and fixed, the alphabet symbol, the number of states, and all that. It cannot depend on the input size, and certainly also not on the parameter. So these non-deterministic steps would only choose among a constant number of different alternatives, fixed and constant. And that turns out to be just an annoying model. You would have to somehow then translate that to allow a certain number of steps, which should somehow be able to depend polynomial on the input size and arbitrarily on the parameter. It gets very messy. And here is easier because you say the non-deterministic step is a little more powerful. It's allowed to guess a number that is unbounded in general. You can restrict it harsher on how many of those you do. So what I'm saying is the details of how the model works for this lecture are not so important. The key step is the non-deterministic guessing step here. It's more powerful. Okay. Then we can define a new class of problems, which is called WP. And the naming will become a bit more clear in a moment. It's the class of all parameterized problems, L kappa, that can be decided by such a non-deterministic RAM. Exactly as we defined it, kappa restricted, which means FPT running time, FPT size of the registers, and at most a function of the parameter many non-deterministic guessing steps. Okay. That's a class of problems. So you can think about what kind of problems are in this class. So how about say our clique problem? The point is, let's try to implement the brute force algorithm on such a machine. So of course we need to use the non-determinism. And what do we guess in the clique problem? Well, k vertices. A subset of size k. How many non-deterministic steps do we need for that? Exactly k, because where we have numbers between, say, 0 and n-1. Okay. So we're using the non-deterministic step to tell us which vertices to pick, and then we're just verifying that it's a clique or check. Might want a name for this set. And that actually takes only time bounded in terms of the parameters. So the whole problem hardly depends on the input size now, on this NRAM. Only this upper bound for the guessing step really needs the input size. And so, well, I guess we can, depending how the graph is represented, maybe we have to walk through the graph to count the vertices. And so the running time would be linear in n, say. Let's be generous and say n plus m only really needed to count the vertices. And then we have k non-deterministic steps. And then we have k squared to verify all the edges are present. Now this is assuming we have an adjacency matrix given, but in this initial time, you could also take any other representation of the graph and transform it into an adjacency matrix, I guess in n squared time. Let's not get fuzzy about the details. Let's just put n squared here for number of vertices. The details here don't matter really. My point is, I just wanted to show you an example of how programs in this WP class look like, because I think it's fairly natural. Apart from this guessing step, everything else could easily be implemented, and the plain brute force algorithm works. It's just that this guessing step now allows us to use the non-determinism in actually a more convenient way than on a Turing machine. It's in a way, it's a more powerful model, it's more convenient to program. It is a bit harder to use in proofs. Okay, certainly this is an FPT time. And the whole thing is kappa restricted. because we only use k guessing steps. So that shows, I guess I posted as a question, so the answer is yes. And most of the problems we had can really be cast in this way. In particular, all the problems where we had, as part of the guessing, pick a subset of certain things, where the subset size is bounded by the parameter. Right? All these graph problems of the flavor of click and independent set, and yes, also vertex cover, less interesting, dominating set. What else did we have? All of them have this property that we're just guessing a subset of vertices, and we can do that in that same way. Okay, so that sounds like a reasonable class. To work with WP hardness, we would need a complete problem, or at least a problem that's that all of that class can be reduced to. The definition of hardness and completeness is exactly the same as always. So a problem is WP hard if every problem in WP can be FPT reduced to it. And completeness adds the requirement that the problem itself is in WP. Now, what could such a complete problem look like? It would somehow have to work. So all we get if we say we have an arbitrary problem in WP is there is such a kappa restricted NRAM. And from that, we somehow have to get a reduction. So the satisfiability problem popped out as the right answer for classical Turing machines, because you can simulate in a Boolean formula how a Turing machine computes. So we somehow need to do something similar here, but we also need a parameter, right? It needs to be a parameterized problem. And if we take sat and look at the number of variables, we know that that's in FPT, right? So that's not going to work. Okay, I answered my own question, but yeah, I guess you would have remembered for sure. So that cannot work. Maybe some other variant of sat is more promising. The key feature we have is we can guess numbers subsets. That's what we've seen in the click example. But that doesn't seem to work too well with sat. Or well, what would that mean in sat to guess a subset? Well, we can guess a subset of the variables. And so a somewhat natural restriction would be that we guess which variables are true, but we bound the number of variables that we are allowed to set to true. And that's the weighted satisfiability problem. Okay? I think I initially mentioned this when we started talking about fixed parameter algorithms as one option for satisfiability, and at the time I didn't try to make it sound like a natural thing. But here, if you come from this NRAM definition, maybe it's not so unnatural that this might work. So the problem is defined as follows. You're given a Boolean formula as for satisfiability in general, and also some threshold k, which is our parameter. And the question now is, can you satisfy the formula with an assignment that, okay, let's be strict, that sets exactly k variables to true? Okay. And we call that the weight of the assignment. That's just the name that gets stuck. I don't know. The number of variables that are set to true. So let's show that this is indeed in WP first. So what would we do to solve that problem? Well, same algorithm as for p-click. Because you're restricted to a weight k assignment. You can guess the subset of variables that you set to true, and then you evaluate the formula under that assignment and see if it is indeed true. Easy. What you can also prove is that a certain variant of this problem is WP complete. Now, in this case, I'll only sketch a bit the proof because WP won't be the final answer for us anyways. It turns out you cannot really make this work. So what we have to do, we want to simulate any NRAM, any, I guess, kappa restricted NRAM. To a weighted SAT problem. And if you try that with ordinary satisfiability, so the Boolean formulas as we know them, this seems not to work. Just because you don't easily get a bound on the weight of the satisfying assignments. But it turns out that there's a slightly more powerful model of satisfiability where this does work, although the details will lead us too far. I just want to sketch briefly what this talks about. And for that, we need to talk about Boolean circuits. I don't know if people have seen this. Maybe in the more technical parts of computer science, you're more used to working with these. The theory version would be you have variables as starting points. And these will have some Boolean value, true or false. Get it a little bigger. And then with the formula, we would normally use, well, we would write the variable many times. Here instead, we can have and OR gadgets, and they can just use variables as inputs. I'm making up this formula now. It probably means nothing interesting, just to make the point. And here you could take this, and this, and this. And so the edges have a direction. They go from left to right in this picture. But the key point is I can use some part of the formula many times. In a circuit, the output, let me maybe add the directions explicitly. So the point is, what's the difference between circuits and formulas? Circuits can be much more compact because if you spell out what I've written here as a formula, okay, I would have to say what the output is, I guess. That's still missing. So this is a single thing that goes in here. And that's not used. That's a bit pointless. Okay, probably this formula is completely nonsensical. The point is you have an input variables as you have for a formula, and you have a single output. But within the formula, you can have sub-expressions. For example, this sub-expression x1 and x2. Oh, I haven't used any nots, right? That's not good. Let's include a not. This just has a single input and output. So there's this part of the formula x1 and x2, and that's used twice. In a formula, I would have to copy it and write it twice. Whereas in the circuit, I can reuse the output of this single gate several times. And that means you can have large parts that are reused, and then the larger reusing parts are reused again. So in general, circuits can be exponentially more compact than a formula. If you had to spell this out as a formula, it might grow exponentially. Which also then on the flip side means working with circuits as an input is often much harder because they can specify more complicated functions with less encoding size. And so you have less to work with because the encoding size is your input size from which the runtime is determined. Okay, so that's a formula. You can always interpret, sorry, that's circuits. You can always interpret a formula as a circuit by just writing it as a tree. So maybe that's worth stating, right? But there's many more tricks you can do on circuits. And the key that we're using here is that you can modify them so that they're satisfiable with a fixed weight. So the idea of the reduction we're given an arbitrary problem. We have to show an arbitrary language L kappa in WP. The claim is that this reduces to this, this problem. So the circ just stands for circuit, just in case it's not circle, cycle, or anything like that. The idea of the reduction is from this, we get, there's an NRAM for solving this. Then we simulate this NRAM with a multi-tape Turing machine to get closer to formula. And then we simulate this Turing machine by a Boolean circuit. That's a similar reduction, as a similar construction as for the proof of the Cook-Levin theorem. And then comes the trick on circuits, which makes the whole point about circuits necessary. We can find the circuit D so that C is satisfiable if and only if D is satisfiable with weight K. So several of these steps are not so clear, right? I didn't tell you really what multi-tape Turing machines are and how we can simulate the word RAM operations. And I also didn't tell you what this trick is. That would lead too far. So it's kind of just a brief outline roughly what this looks like. Let's claim that's a bit of a proof, but that's roughly what it would go like. So it has similarity to classical complexity in some sense, but you have to do a few further steps to get the weighted satisfiability. The point why I think it's not worth digging through the details here is that this is not the final answer. Yeah, I don't think I have a nice example here. The problem with WP is that it still seems too powerful. The key problems that we were looking at, say p-click, is part of this class. But it seems that we cannot actually reduce this problem p-sat circuits to p-click. In a way, the circuits are too powerful, and this WP complete problem is too powerful to be simulated with something like p-click. If you were wondering how to do that, I guess it's subject to some complexity theory assumption. It isn't possible. P weighted sat of circuits. Did I put that in normal parentheses? Okay. So the not here is important. I don't know. That doesn't seem to work. So we found a class with a natural complete problem, but it seems it's too hard a problem. Shall we do our break here? Already 11 again. It's a bit of a shame. Things get concrete and nice now only. I think this WP part, I didn't want to kick it out because it's kind of the more natural first attempt and basis of what comes next. But it's a bit unsatisfying in that we can't actually do the details. Okay, time to move on, I think. I'll try to have some time to get to some actual nice reductions. But let's set up the theory for that first. In the next section, we'll look at a further restricted model of computation. And intuitively, the motivation for this is if you go back to how we use the NRAMs in our examples, say the p-click algorithm, we guessed the random vertices. And in a way, we imagine we first guess and then we verify. But if you think about it, the verification was actually in the click problem very fast. It only depended on the parameter. And in that case, we could have said that actually only the last few steps need the non-determinism. In this problem, this was a bit of an extreme example. If you think about the circuit satisfiability, by contrast, you have to pick the variables and then still evaluate the entire circuit. That's going to take more time. So you cannot easily push that all the way to the end. And that maybe gives some intuition for the distinction there. And so the model that we'll look at does exactly that. It has to do the non-determinism at the end of the computation. So that's called tail non-determinism. As we discussed, this WP hard complete problem is too hard. So we have to restrict the class a bit to only keep the slightly simpler problems. So an NRAM, as before, kappa restricted NRAM for a problem is tail non-deterministic if these non-deterministic steps occur in the last so and so many steps, depending only on the parameter. That's the important part. So h, again, is an arbitrary function, but it only depends on the input via kappa. Okay? So as before, NRAM, the number of non-deterministic steps is bounded, but it has to be at the end of the computation. And it turns out this is the final answer for our reductions. It gives rise to this complexity class W1. So these are all the parameterized decision problems L kappa that are decided by such a tail non-deterministic kappa restricted NRAM. It's a bit of a mouthful. And if you wonder what the 1 comes from, that's from an alternative characterization of the same complexity class, where this is a parameter where other numbers can make sense as well. But the point is that this needs a lot of logic and terminology from Boolean circuits and so on that in the end is not used for anything. So instead, I'm using the alternative characterization where only W1 really makes sense. That's the downside. But the definition is more natural. It's just the class that allows such algorithms, non-determinism, bounded by the parameter, and only at the end of the computation. Hardness and completeness, just as before. A problem is W1 hard if every problem in W1 can be FPT reduced to it. And completeness adds that it has to be in W1. Now, how can we get to a complete problem this time? And it turns out this is maybe a more natural complete problem than the one before, which is also why we can do the full proof. So that's the problem. It's called the K-step halting problem. Now, people with some theoretical computer science background will remember the halting problem for Turing machines, the infamous problem that is not at all computable, namely deciding whether a Turing machine on a specific input terminates or runs into an infinite loop. That is not possible with any computing device we can think of. And the same is true by reductions about all programming languages that are Turing complete and so on. Now here, we're looking at the halting problem, so there should be some alarm bells in your head ringing. But we restrict the problem so much that it actually becomes solvable. So the input is a Turing machine, an ordinary one, no fancy things, but it is non-deterministic. And it has some input that is also given and this parameter k. And the question is now just, does this Turing machine accept the input? Does it terminate? But after at most k steps. If it keeps running for more than k steps, we're allowed to say no. Okay. And that's, of course, what makes the problem decidable. You can just simulate the machine for a certain number of steps, and then there's two options. It finished or it didn't, right? No infinite loops in the decision, and so that's what makes this problem solvable. So some subtleties about this problem. I guess we would have to somehow specify how we encode a Turing machine as an input to a problem. Remember, it has to be encoded as a language somehow. You can invent various ways to do that, and basically they'll be okay. Both the state space of this Turing machine and the tape alphabet and all components of this Turing machine are now part of the input of our algorithm. So from the perspective of an algorithm that tries to solve the k-step halting problem, it cannot assume that the Turing machine it's going to get is of finite size. Once we have that machine and we start simulating it, it is finite, but we're given the machine itself as part of the input. So that means because the alphabet could be that big, or the number of states could be that big, we can have up to n different non-deterministic choices in each step when we simulate the machine. So what I just sketched, taking that machine and simulating it for a while on a Turing machine, that's already somewhat expensive. It doesn't look like it's in FPT, for example. You would need to spend n to the k plus 1 steps at least, because that's the number of possible non-deterministic paths you have to follow. A side remark is we don't actually need an input here to be given. The problem doesn't change if you assume that there's no input and the machine just has the specific input we're talking about baked in. You could augment the machine so that the first part of its program produces that input because it's a fixed one, right? We're given the input to the k-step halting problem is a fixed machine and a fixed input. So you might as well combine them. That's a convenient little simplification. Now, the key result that we want to prove is that this problem is indeed a complete problem for our new class W1. And so, yeah, I guess I should stress that the number of steps is the parameter we're looking at. I think I mentioned, but that's important. Okay. Now let's spend a minute to prove this, just because I think it's instructive to see how these things work together. There's two parts, because we're claiming W1 complete. The first part is W1, this is in W1. That's hopefully the easier part. So we have to show that the problem of computing these k-steps can be done with such an NRAM. So the input to the problem is a Turing machine M, an input X, and the parameter K, or the steps K. And we'll basically use an NRAM A that simulates that machine. That's relatively easy. We basically follow just the instructions of the Turing machine. Now, I said before, from the perspective of this NRAM, Turing machine can be of unbounded size, and it depends on it's given as part of the input. But that's not a problem because the NRAM also has the register contents also can depend on the input size. The bigger the input, the larger numbers it can handle. We also have to show that this NRAM is kappa restricted and tail bounded though. For kappa restricted, how many non-deterministic steps do we need to simulate such a Turing machine? Well, at most k, because we're only simulating it for k steps. And we have some leeway. It could be a function of k in case the simulation is not perfectly getting one random step in the Turing machine simulated with a single step. But certainly we're not running the machine depending on the input size. It's just running depending on the parameter. And tail non-deterministic follows in the same way. We're running the machine for k steps. We might have to do some pre-processing to get the simulation set up. That might depend on the Turing machine size. But then the actual steps only depend on k, how often we have to do it. And copying the output is constant time because it's a decision problem. It's only yes, no. This is in a way, same argument, and these can come last. And copying the output is fast as well. Okay, so here that's the trick, that the simulation itself is bounded only by the parameter. That was the first bit. Now, we also need to show that it's W1 hard. And for that, we need, given some arbitrary problem in W1. That means there is an NRAM for this. Which is kappa restricted, tail non-deterministic, and we have to show that we can solve. Can output the same as this machine A using our problem of simulating k steps of some Turing machine. How are we going to do that? So when you try to simulate A, then A is given some input, some word that could be in the language L. A on Y. Well, the k-step halting problem. K-step halting problem. Let me abbreviate that. So what we construct So we have to give a reduction now that takes this input y. So we want to show that L kappa is FPT reducible to our k-step halting problem. So the input to the reduction is y. And what is fixed is A. That's outside of the reduction, right? Because the problem is in W1, we know there is some non-deterministic RAM that decides L. The reduction that we map here, so given this input y that we would feed to A if we were to run that program right away. So we take this y and now we run the machine A for its deterministic part. Deterministic part. And now here comes the magic. The deterministic part can be polynomial in n. No, it can be FPT, but we're doing an FPT reduction. That's fine. So that has FPT running time. But it's deterministic, so there's no choice. It's good enough to run this once at the beginning, and then we take a snapshot of the machine at this point. And basically we encode that. Well, what is the state of the machine at this point? It's the memory contents and maybe an internal state, a program counter, right? So this is memory and register contents. Plus where in the program you are. So we can take that and write that down and construct now a Turing machine that simulates the non-deterministic tail of A. Okay, so that's going to have some slowdown. But again, here the Turing machine, we can give it a number of states that's big enough to represent the number of non-deterministic choices that A is doing, because we're constructing that as part of the input. So I should say it's a non-deterministic Turing machine. And we know that this tail has h of kappa of y many steps. That's from the definition of kappa restricted. There's some function h. So we know for how many steps we will have to run this Turing machine that results from that. If it finishes in that many number of steps, then A would have accepted the input and we can copy the output. Otherwise, we can stop and reject the input. So the output of the reduction now is this Turing machine . The Turing machine and then the number of steps we have to simulate it. And so you can check that this is an FPT reduction. It runs in FPT time because we run A for FPT many steps. We construct something that's I guess the machine A is not even part of the input, it's constant size. And the number of steps is the parameter of the new problem. The number of steps is a function of the parameter of the input. So it's parameter preserving. Okay. And I guess the correctness is almost obvious. The way we construct it, if that machine terminates with that many steps, then A would have accepted input Y and vice versa. So that part here is relatively boring. Maybe we should write down it's an FPT reduction because the reduction takes FPT time. That's from this part up here. That's parameter preserving. That comes from here. And the correctness belongs here as the next component, is essentially by construction. Okay. Not too much time left for nice reductions. But let's zoom out a bit again. So we have the class W1. To remind you, it's the class where you have a tail non-deterministic kappa restricted NRAM that decides the problem. And we found there is indeed somewhat natural complete problem for the class, namely simulating now a standard Turing machine, a non-deterministic one, for a given number of steps, where the number of steps is the parameter. So what can we do from this? We don't usually care about this halting problem. We want to decide more combinatorial optimization problems. And to get to those, we need some intermediate problems to translate away from the machines. And here weighted SAT can be shown to have a variant where this is indeed W1 complete. And so the variant here is, again, the parameter is the weight of the assignment that you have to put, but now satisfiability is a specific normal form for formulas. And in particular here, it's a 2 conjunctive normal form. So it's the same as in 3SAT, but with 2 literals per clause, which is a bit awkward if you remember, because so 3SAT was NP hard. P complete, but 2SAT is in P. But it turns out if you ask for the weighted satisfiability, that is no longer such an easy problem. And indeed, the parameterized problem where you ask for, can you satisfy a formula in 2 conjunctive normal form where the weight has to be exactly K? That turns out to be a W1 complete problem. So which in particular means it's got to be NP hard, right? So to prove this, we have to go. I don't think I've included the proof for this theorem. I'll look into how hard that was. Maybe it led too far. It turns out that this problem still is a bit inconvenient to do reductions from. And you can restrict it a little further, where all the literals are negated. So all the inputs are of this form. You have some not x1 or not x2 and not x3 or not x2 and so on. So all the formulas look like this. It's two things, but you take the negation for all of them. And it turns out that's also W1 complete. And from that, we can do sensible reductions. Okay. So I suppose, again, here going back to the weighted satisfiability needs more logic than algorithms. And so let's not do that. But instead, let's as one final point, at least see one interesting problem that we've started a long time ago with, and see that it's W1 complete. And that's the independent set problem. So parameterized independent set in exactly the same way as we defined it before. The canonical parameterization is the number of elements in the set. As always, the proof has the two parts of in W1 and then the hardness. For in W1, same as for p-click that we've argued before. We use k non-deterministic steps. Of an NRAM. To guess a subset. Of the vertices, and then we use k-squared time to check that there's no edges. So that's kappa restricted because we only do k guessing steps, and it's tail non-deterministic because everything that comes after the guessing is bounded by a function of the parameter only. Okay, so indeed the problem is in W1 because you can solve it with a kappa restricted, tail non-deterministic, NRAM. Good. Interesting bit is the hardness. And for that, of course, we borrow one of the problems that we know to be complete already. So we take the PWSAT 2CNF minus problem. I know it's lovely to juggle with these names. We prove PWSAT 2CNF minus can be reduced to our beloved independent set problem. So what do we have to do? We have to construct a reduction, and we have to embed our 2CNF minus formula into somehow a graph. So we're given an instance of this problem, which is some formula. Let me write it like this. There's some variables. Sorry, it's some pairs. Let me maybe comment on this first, because the problem is so restricted. The way a clause looks like is totally specified by two numbers, namely the indices of the variables. Everything else is fixed. It always is negated, and it's always exactly two literals. So the formula always looks like one big AND over some set of pairs, and then each clause is xi negated or xj negated. Okay. And from that, of course, that's one input, and we're also given the weight k, the target weight. And now we have to construct a graph from this. As input to the independent set problem. As vertices, we just take the essentially the variables. And the edge set is the set of all these clauses, if you want. So it's all the combinations where ij is in this set I. When I say you're given the formula, you could essentially just write down this set of pairs, right? That fully specifies the formula. And so we take that formula and we make every clause an edge. If you want to satisfy this formula, you have to make all clauses true. And a clause is true if one of the literals is true, and a literal is true because it's negated if the variable is false. Okay? So setting all the variables to false would make the whole formula true. Seems like an obvious problem. But weighted satisfiability says exactly k variables have to be set to true. In this case, it's important that this is an equal. And so the problem really asks for choosing the right set of variables. And so if I pick an independent set in this graph, I'm picking a set of variables where there's no clause that connects them, which means there's no clause where two variables occur that are both set to true simultaneously. I'm only picking a set of variables, a set of vertices in this graph, where there's no clause that connects them. So all of them only appear in clauses where there's some other variable that I don't set to true. So the clause is still satisfied. Okay. So if G has an independent set of size k, I guess, yeah, I should have said the parameter stays the same. And these variables and no clause contains two true variables. So phi is satisfied. And vice versa, if you have, that's the correctness in one direction. In the other direction, if phi has a satisfying assignment of weight k, then the true variables are an independent set in G. Otherwise, the formula would have a false clause. Okay, so the reduction is actually not super interesting. The tricky bit is how to get to the right weighted satisfiability problem. Okay. We'll look at a few other examples in the tutorials. There's one more reduction that I put on the slides, which is talking about a slightly different problem, which turns out to be a good intermediate problem. That's the partial vertex cover problem. Let's at least briefly introduce it. So as the name suggests, it has to do with vertex cover. But now we're given both a size for the number of vertices, the set of the vertices that's supposed to cover edges. But I'm also giving a threshold for how many edges they need to cover. Previously, that was all edges in the graph. In this problem, you can say, it's fine if they only cover 10 edges. So it's a generalization of vertex cover. And remember, vertex cover itself is FPT. So we wouldn't expect it to be a hard problem, a W1 hard problem. But you can show that this partial vertex cover problem is indeed W1 hard. And we can do a reduction from independent set. But I don't know if we have enough time to do that. I could briefly sketch it. Maybe just by picture. So how would we do it? So we're given an input for the independent set problem. It's a graph. And a parameter k, how many vertices we want in the independent set. We keep the same graph. We set t, the number of edges we want to cover, to be k times the number of vertices. So sorry, that's not, we don't keep the graph. That's the other reduction. So we have vertices and edges. The number of edges we want to cover is k times the number of vertices in the input graph. But the new graph consists of the old graph, and then for each vertex we add some vertices wvi, where this ranges from from 1 to the number of vertices minus the degree of that vertex. And the edges are the old edges, and we have to connect these up. So basically create a star. We connect V with its WVIs. Same values for I. So how does that look like in some, that's not what I wanted. Closer from the beginning. Right. Let me just draw the example. So here's our input graph, where we ask for an independent set. Say we want 2 vertices in our independent set, this and this. And that's the largest. And now we fill up in this In this graph, there's 4 vertices. Every vertex, that's the construction here, gets a number of pendant vertices added in the reduction, which is the number of vertices minus the degree. So this guy has just 1 at the moment, so we fill it up to have degree 4. This one has 2, so we fill it up with 2. This has 2, and this has 3, so it only gets 1. Okay. The choice of our threshold for how many vertices we're supposed to, how many edges we're supposed to cover, is chosen so that we have to cover with every vertex that we pick exactly number of vertices in the original graph, many edges. And you see that this is only possible if you pick what was an independent set in the original graph. If you pick the red vertices, then all the vertices here, the resulting graph is regular. So G prime is size of V regular, which means all the vertices have the same degree. And then the best way to cover edges is if the edges are disjoint. If there's no edge between any 2 red vertices, then every red vertex covers size of the vertex set many new edges, and they don't overlap. And that's exactly the case when the selection was an independent set in the previous graph. Okay, let's leave it with that. And you'll see some other reductions in the exercise sheets.